Most plant creation technologies like SpeedTree utilize procedural generation. This technique creates 3D geometry according to specific mathematical equations with a wide variety of variables. These algorithms can produce unique, high-quality assets far quicker than traditional modeling techniques. It's a non-destructive workflow which makes future modifications and variations painless, and extra steps like UV unwrapping and vertex weighting for wind simulation are all automated. Needless to say, it's a powerful tool for artists, especially considering the importance of saving time during the game development cycle. However, there's one major downside. With mathematical equations driving the shape of a generated mesh, understanding what each parameter does is important and necessary. But for new artists, this drastically steepens the learning curve, making the whole process far more daunting. This complexity also bleeds into the software development side. A lot of study and research has been dedicated to the procedural generation of trees. In fact, that's why there are so many alternatives to SpeedTree today. However, for other types of vegetation, hunting down usable algorithms becomes far more challenging. As such, if I were to take the procedural generation route for PlantLife, most of my time would likely be spent in mathematical theory. Fortunately, there's an alternative. Kitbashing is a popular modeling method widely used throughout the game development and film industry. Artists use a library of pre-prepared component meshes and combine them together to create new models. While this is predominantly used for buildings, the concept can easily be applied to plants. The problem is the risk of repetition. After all, no one likes seeing the same assets being used across multiple projects, as it kills any sense of originality. One solution is to have a wide variety of shapes to increase the number of potential combinations. For example, a mushroom made up of 5 parts with 15 possible shapes for each results in over 360,000 potential combinations. But that's not enough. This is where distortion enters the picture. After a model has been assembled, a procedurally generated Perlin noise map can be applied to displace the generated geometry. This skews and stretches the vertices to produce a similar but ultimately unique plant shape that eliminates the limited combinations problem. Distorted kitbashing isn't as fancy as procedural generation, and for hero assets it's likely unsuitable. But for game developers looking to populate their scene with background foliage, it's a perfect fit. The software is far easier to learn, but most importantly, the time spent generating plants drops from a few minutes to seconds. In fact, by the end of this video, PlantLife will be generating mushrooms within a single click. Before getting to work on the generator, I need to make some changes to the project's code architecture. As I explained in the last devlog, each node tree is stored within a list. This enables PlantLife to have multiple projects open at the same time. However, to keep things tidy, I created a new plant class. The plant class now contains the node tree of each project along with additional functions to generate and draw a plant model using the settings within that node tree, while the original list of node trees is now a list of plant pointers. In the long run, PlantLife will be capable of generating countless types of plants, but to kick things off, I decided to start with mushrooms. As foliage goes, these are relatively simple, consisting of 5 primary components. To represent these in the node tree, I repurposed the stem node I made in the last video, and I also added 3 additional nodes for the other mushroom components. After digging up an old copy of the Usborne Spotter's Guide to Mushroom and Fungi, I got to work making some of the primitive shapes for each fungus node that will be fed into the distorted kitbashing system. This took a few days, but eventually I finished creating a wide range of assets using the illustrations from the book as a reference. With a library of shapes now prepared, it's time to crack on with the plant generation system, starting with the seed node. As a reminder, the seed node is responsible for initial positioning, rotation, and scale, but most importantly, it determines how many plants should be generated across a specified area, with minimum distances between each placement. That way, artists can generate entire patches of vegetation rather than just a single asset at a time. Generating a random value for rotation and scale based on minimum and maximum values is simple enough. However, calculating placements is where things get more complicated. The area in which plants can be placed is a circle defined by a radius. To generate a random point within this circle, it may seem sensible to generate a random value between 0 and the radius, along with a random angle between 0 and 360 degrees. However, this approach won't actually produce truly random results, since most placements will be biased towards the central point. Instead, I want to generate a random uniform distribution and then convert it from polar into Cartesian coordinates. This can be a little tricky to work out for the first time, but at the end of the day, the math is relatively simple. With random positions sorted, it's time to introduce separation. To stop 2 placements from being on top of each other, PlantLife cross-checks with other placements already calculated. If the distance between any existing placement falls outside of the specified separation range, the placement fails, and the software will then try again. This brute force method obviously isn't the most efficient, and in some instances it will likely take some time for a viable placement to be found, especially for dense foliage. After all, it's the equivalent of throwing things at the wall to see what sticks. Therefore, after 5 attempts, if no placement has been found, PlantLife will simply give up and move on. This is to prevent getting caught in an endless loop, and the software will output a warning to the artist to alert them that the parameters they've set may be unviable. In the future, the number of attempts will be adjustable by the artists if I don't find a better solution later down the line. With the spawn transformations now calculated, they need to be stored in an accessible manner. To achieve this, I created a new plant component class. Apart from having the individual values for each transformation, the plant component class also contains a pre-computed 4-dimensional matrix. This matrix contains the same transformation data, but in a format that can be directly used by the GPU. This does result in duplicate data being stored inside the class. However, the memory impact is negligible, and since the matrix is being calculated in the generation stage rather than in the render loop, the drawing speed is increased significantly. With a wide range of shape options for each node, artists need an intuitive way to select the ones they want to use. And after experimenting, I decided to use a drop-down checklist UI editor. It took some finicking, but using one of Teleric's controls, I was able to integrate this custom editor into the property grid system. Artists can now easily toggle which shapes they want to use, as well as search for a specific one. In the future, I plan to modify the editor further to include an image tooltips to preview the geometry of each shape, since that's far more informative than just a label. After the artist selects which shapes they want, the plant generator will randomly pick one from the selected list, and stores the pointer to the model data inside the newly created plant component pointer, along with all the calculated transformations. The last piece of this puzzle is actually loading the model files themselves. Since I'm using my Bright Engine SDK, this step is relatively straightforward as it handles 3D asset loading as well as memory management for me. However, Bright Engine is designed to pack data as efficiently as possible. As such, accessing the model data via the resource manager is tricky unless you know the exact memory address where it's been stored. So to make my life easier, I created one final class. This class effectively serves as a collection of pointers for the model data of each shape, stored inside a series of maps. This means that model data can be queried by an assigned label, and there's no need to waste CPU cycles manually searching through the resource manager. PlantLife will preload all available model files on startup. While this does increase the initial loading time for the software, it prevents stalling during use that could disrupt user experience. To keep loading times as low as possible, it's paramount to use the right 3D file format, and after some initial testing, Autodesk's FBX proved to be the most optimized for now. The last step in the generation stage is to stitch all the individual component models together. My initial tactic was to use skeletal rigs. Unfortunately, this quickly proved problematic. The Bright Engine SDK uses a reverse-engineered FBX importing system rather than the official Autodesk one. As such, it only loads a bone's transformation matrix as an offset from its parent. But for PlantLife, that's less than ideal. It's possible to calculate the world space transformations by stepping through the skeletal rig and multiplying the offset matrices one by one. However, this isn't particularly efficient and can lead to a confusing mess. Using the official Autodesk SDK would easily solve this problem, since it's possible to access bone world space coordinates directly. But the file format is proprietary, and while Autodesk has made this tool available for free, the recent scandal surrounding Unity serves as a perfect example of why creating software using someone else's technology can potentially create serious problems later down the line. It's also worth pointing out that storing skeletal rigs inside of model files can drastically increase file size, causing longer loading times. So instead, I created a simple custom metadata archive that stores the world space bone data for each component. This does create an extra step, but it keeps the model file sizes small, eliminates the need for third-party technology, and simplifies the entire stitching code. Building a node tree doesn't take long. However, the ultimate goal of this project is to allow artists to create 3D plant models instantly, and that's where the Generate button enters the picture. PlantLife will store a collection of template node trees for different plant types. Whenever creating a new project, the artist will select which kind of plant they want to make from the drop-down list and then hit the Generate button. The software will then instantly load up a template node tree with each variable randomized to create unique design every time. At this point, the Generate button will turn into a Randomize button, and clicking on it will randomize the settings of each node within the tree as many times as the artist wants. The idea is to create different looking plant geometry quickly without having to adjust each setting one by one. These template node trees are designed to provide completed assets. However, there's nothing stopping users from adding or removing additional nodes to create weird and wonderful vegetation. Of course, randomizing variables can lead to some pretty wacky results, and it will take some time to find the ideal range of potential values for each variable. This is something that will require persistent testing, and may take some time before eventually producing consistently usable results. Don't forget to subscribe if you want a free copy of PlantLife once it's finished, and as always, let me know your thoughts in the comments below. I'll see you in the next one.